Okay, welcome back to this channel again. In the previous video, we discussed about the atomic radius across the period. So now we're going to continue with discuss about how about the changes or the trend of the atomic radius when going down the group. Can we still using the effective nuclear charge to do the explanation? So let's calculate the effective nuclear charge for the element in the same group. Okay. Lithium, sodium, potassium, all these three are very common elements in group 1. So when we write out the electron configuration for all the three lithium, sodium and potassium, these are the electronic configuration. Once we want to determine the effective nuclear charge, we still need to remember the formula proton number minus the number of inner electrons. Okay, so for lithium, the inner electron is in period 1, while for the sodium is in period 1 and 3, while for the potassium is period 1 to period 3. Okay, so all these three elements, even though they are in the same group with the different number of protons, but all these three have similar effective nuclear charge, which are the positive one. So it is very obvious that we are not suitable to use effective nuclear charge to discuss about the trend or the variation of the atomic radius down the group. Okay, but we notice that the number of shells occupied by electron is increasing. Okay, this is our observation because for the lithium, 2 shells occupied with electrons, while for the sodium, 3 shells occupied with electron, and lastly, the potassium, 4 shells occupied with electron. So we can get the idea that once the principal quantum number increase, the shielding effect also increase and will cause the size become bigger.
Okay, now let's continue with the explanation. When going down the group, more shells are occupied by electrons. For example, here, if in group 1, electron in shell n equal to 1 will shield the electron from n equal to 2. While for the outermost shell n equal to 3, the electron will be shielded by n equal to 2 and n equal to 1. Okay, electrons in the inner shell shield the outer shell from the nucleus, at where we say that the shielding effect by the inner electrons are increased. When this case happens, means that effect of mutual repulsion electrons between shells also increase. Mutual repulsion in here means that penolakan sesama elektron, okay, antara shell, between the shells is increased because electron possess the same charge, so they are going to repel each other. Okay, when the repulsion happens, the strength of the attraction of the valence electron with the nucleus will become weaker. Okay, so here we have to emphasize valence electrons because when we want to discuss about the size, we have to focus that the distance between nucleus and also the valence electron. Okay, due to the repulsion, so the attraction become weaker. So this means that the distance between the valence electron and also the nucleus will increase, means that they will become further apart from each other. So then lastly will means that the size of the atom is bigger. Okay, now let's look at one question. This is a question from ChemFrame, question 22. Okay. So in this slide, we are going to focus on question number 2 only. Between element Q and S, state the element that has the larger atomic radius. So when we look at the electron configuration Q and S, both of these elements, they are considered in group 14, okay, because they have group 16, 1, 2, 3, 4, 5, 6, 6 electrons, 6 valence electron. So, and then p block element, so that's why the group number is group 16. Same case happened to the s element, 1, 2, 3, 4, 5, 6. So both of these element q and s are element in group 16. So then we have the idea that we are going to discuss going down the group. Okay, we are going to apply the trend of going down the group. So just recall back, when going down the group, the shielding effect is increased. Once the shielding effect is increased, means that the atomic radius will become bigger. So in this case, they ask us which one have the larger atomic size. So the answer is S, element S. Okay, after discuss the trend down the group of the periodic table, now we are going to discuss the atomic radius across the first row of transition element. Okay, generally, if you recall back what we learned in the previous video, across the period, supposedly the size is getting smaller. Okay, but then we notice that there is a trend that different from what we predicted, especially for the transition elements. Okay, so that's why in this slide we focus on the transition element only. So additional electrons are entering to the 3D subshell, and the electron in the 3D subshell will help to shield, okay, or still remember the word block the 4s electron from the nuclear charge. Okay, so now let's look at the electron configuration. If you notice these 4 elements with the proton number 21 up to 24, all these 4 atoms, actually they are transition elements. Okay, and when you look at their electron configuration, you will notice that 4s, all these 4 are end with 4s2. So means that even though the proton number is increased, means that electron also increase. At the same time, when the electron is increased, we notice that actually all the electron is adding to the 3D orbiter. Okay, like state in here, additional electrons are entering to the 3D orbiter. Okay, and the 3D orbiters will help to shield or to block the 4s, the electron in the 4s, to reach the nucleus. Okay, so in this case, generally when we look at here, we will notice that the electron configuration looks like the quite similar, okay, at where the means that the shielding effect is not obvious. So we may think of we need to use effective nuclear charge to explain when the question is asking about across the period. So when we use the calculate the effective nuclear charge, we notice that all these 4 transition elements are with the positive 2 or as the effective nuclear charge. Okay, so that's why we come out at here, the effective nuclear charge remains fairly constant. Okay, it's considered constant across the D block element. So again, this time we are focused on the transition element, which means it's the D block element. Okay, after discuss about the effective nuclear charge, because just now we already have the idea there are 2 factors which will affect the atomic radius. One is effective nuclear charge, another is shielding effect. Okay, so now let's focus on the shielding effect. At the same time, the shielding effect does not change much as well. Why? Because the number of shells that occupied by electron are still the same. Okay, we can check it out throughout the electron configuration. So all these four, the element occupy 4 shells. Okay, all are end with the 4s2. Okay, so by combining these both factor of effective nuclear charge and also shielding effect, so again we can make a conclusion: the size of the atoms do not vary significantly for transition element. Okay, so significantly in here we can say that it is like ketara. Okay, in bahasa, vary is like berbeza. Okay, so perbezaan across the period for the transition element is not significant. Okay. Okay, up to this moment, we already discussed 3 conditions. First condition is across period, which is focused on the transition element. Okay, so if we look at this graph, the transition element is around here. Okay, so when we look at here, so we notice that the change of the atomic radius is not significantly different. Okay, so that's why we come up the conclusion does not change much. Okay, beside from the transition element, we also will go through across the period. We notice that the size is getting smaller because of the effective nuclear charge is increased. While going down the group, the size is getting bigger due to the shielding effect increase. Okay, so if we continue here, why the elements of the transition element does not change much is because of both effective nuclear charge and also shielding effect does not change significantly. Okay, so we also can use the term significantly. Okay, so we will stop a while for here. In the next video, we are going to continue with another type of the comparison, which involve the atom and also ion. Okay, before we end this video, let's look at one question. Okay, roughly this question is from Ken Friend as well, which is a question 32. However, the question here is not exactly from question 32. I only take the figure here to do the discussion. Okay, so question number 1, which of the element above has the largest atomic radius? So means that we are going to use the conclusion that we learned in the previous slide. Across the period, the size is getting smaller. While going down the group, the size is getting bigger. So the question is asked us which one is the largest. So that's why the answer will be going down the group. So the element T has the largest atomic radius. Okay, question number 2, they are going to ask us what is the smallest atomic radius. So basically at here we will consider that the smallest atomic radius is the one which is at top of the right hand side. So in this case will be considered as Q. Okay, last question that we are going to answer here based on the figure 1 above. Arrange the element in order of decreasing atomic radius. If you still remember previously we say this element T has the largest size, while element Q have the smaller size. Okay, So the question here is want us to give the decreasing atomic radius. So means that the largest is the T, while the smallest is the Q. Okay, so at here, then we will look at S is smaller than T. Okay, then we have M, P, and R. All these three are in the same period. So we have to apply the idea across the period. The size is getting smaller. So and then so means that the bigger size here is the M. So M bigger than P and then P bigger than R. The smallest is the Q. So this is the arrangement from the largest atomic radius to the smallest atomic radius. Okay, so we will stop the video at here and then we will continue with another video which we are going to compare the size of the atom and also ion, and then another one part is about the isoelectronic species. Thank you for watching.